Well, thank you very much for coming this afternoon, and hopefully this will go quickly and we'll get this underway. May I have the next slide, please? So just to let you know that we do have the credentials to talk to you about flying in the Andes. Only in the year 2012, we flew over 100,000 line kilometers on 40 different projects in Argentina, Chile, Ecuador, and Peru on surveys that had the listed specifications. So they were mostly magnetics and mag spec. We used typically A-star 350B3. A few were done with Lamas. Line spacing was typically 50 by or 50 to 400 meters. Most of them surveys were done at 200-meter line spacing. Average survey height was 30 meters off the ground, and we did some up to as high as 50 meters or 60 meters off the ground. Average project size was somewhere around 2,500 linear kilometers. Survey altitudes ran from 3,000 meters to up to 5,800 meters, or about 10,000 feet, up to almost over 19,000 feet. Typical survey ran in the range of 3,500 meters to 4,500 meters. Our bases were set up as high as 3,800 meters, or over 12,000 feet, the base operations. Next slide, please. So the topics I'm going to deal with today are how to choose what kind of actual aircraft should be using. I'm going to obviously choose helicopter in the end, so then we'll look at what type of helicopter you should be using. What kind of configuration would you be using in terms of whether it's a bird or a Stinger configuration? That's important detail. And then what are the flying realities, speed, obstacles, fuel loads, things like that. And then I want to look at some data issues that are involved in flying helicopters and in the Andes, which produced its special cases. Next slide, please. So this is a small project, well, part of a larger project that we did in Peru. This shows you the terrain, and the purple lines are the actual drape flown by the helicopter on this site. If I have the next slide, please. This is what would have been flown if it had been flown with a fixed-wing aircraft. Next slide, please. This is the same area from a different angle. You can see how the helicopter lines really drape the property very well. The next slide will show what you would get if you're flying in an airplane. Clearly, this kind of work in the high Andes with so much terrain variation, if you want to get any real kind of detailed data, you're going to have to use a helicopter. And if you want any radiometric data at all, you're going to have to use a helicopter. This valley is well over 1,000 meters deep, so clearly you're way out of range if you're trying to get radiometrics. Next slide, please. This again will show the same area, but this time on the left is the planned drape of a fixed-wing survey, and anything over kind of orange is over 1,000 feet, where you start to lose all radiometric information. This is the actual achieved terrain clearance with the helicopter, and you can see that the entire survey is well within, very close to the ground. Now the next slide, please. It's difficult to decide what is going to be your ultimate survey height with a helicopter. I mean, clearly we're going to have to use helicopters, so it's hard to predict because one would fly with variable speeds. So you can look at these different ones. These are at different speeds as you move down from 120 kilometers an hour down to about somewhere around 80. Clearly you want to be able to fly the thing with variable speeds so you can take advantage of the actual nature of a helicopter. Next slide, please. Again, this is what can be achieved with a helicopter under the circumstances if you're prepared to fly the survey with variable speed and carefully. Next slide. So how do you pick which helicopter you're going to use? Well, what's very important with helicopters is the ability to take off. And the way you can tell whether you can take off or not is your hover underground effect. If the helicopter can't hover, it can't take off. So if you look at the actual helicopter data here, you can see that the Hughes 500, R-44, Bell 206, these helicopters can't take off above 12,000 feet. So it's like Hotel California. You can check in, but you can't check out. Because clearly they can fly that high, but they just can't take off. As you move up, you see other helicopters. The Bell L3, it supposedly has some higher range. We've found that it really doesn't have these kind of characteristics. It's not very suitable for flying above 3,000 meters. And then the A-Star 350B2, it appears that it should be adequate. We haven't had a lot of experience with it because these helicopters are not very popular in the Andes because there's a better helicopter to choose from. So the one that the suppliers use is the B3, which is clearly has the altitude flying heights. It can leave the ground easily, so it's suited. And as well as the older Llama. We have difficulty using that because of its airframe age, and a lot of companies aren't interested in a 50-year-old aircraft. Twin-engine aircraft are often asked, why weren't we using twin-engine? Two-engine must be safer. Well, in fact, it's not. None of these aircraft would be suitable with twin engines. They may be all right for going out to a fuel platform, but they're not going to get you off the ground at altitude. So if anybody's thinking that twin-engine aircraft on helicopters is going to be safer, it's not. If anything happened, you go straight down. Next slide, please. So we end up choosing the A-Star 350. So what does that mean? Next slide, please. Well, we're going to have to decide whether we're going to use a Stinger or a bird. A bird mount has always been the popular one in the old days. We used to use that a lot. You didn't need to get it certified. You could build one in your garage. Didn't have to compensate the data, and the signal was relatively clean, and of course it was not expensive. The difficulties is you needed to train the pilot to carry the load, frequent collisions with ground and cables, so there's considerable safety risk as well as financial loss. And unfortunately in the mountains, you end up slowing down, speeding up, and so forth, so you get a spectacular bird swing, which can produce unpredictable long wavelength noise of up to 3 gammas below an A-Star. So clearly it's not the satisfactory mode. So we go for the Stinger. These are more expensive. They're safer to fly because, of course, they're hooked onto the helicopter, and the pilot doesn't have to worry about what's going on. He just flies his helicopter. The data is ultimately much better, and we'll get to that. And, of course, the radiometric platform is closer to the ground because you don't have to keep 100 feet above the bird. The cons are they're more expensive, requires preparation, aeronautical approvals, and so forth, and this is expensive for the people that don't want to make the investment. You also need a sophisticated data acquisition system, and processing is required to deal with the noise of being very close to the moving parts of the helicopter, which then is rotor noise, which we'll deal with now. May I have the next slide, please? So you got this magnetometer very close to the helicopter. Can we compensate it? Well, the answer is yes. This is a typical compensation curve of a AS350B3. It results in 1.62 compensation. Some are worse, some are better, but this is clearly adequate for the purpose, and you can see that the data is well compensated, so that we can put a magnetometer very close to the moving parts of a helicopter and get away with it. Next one, please. Next one, please. Can you run this video? This is the same area, but it shows, I just wanted to fly through this area so you can get a feel how the flying ended up. These are the actual flight lines taken from the digital database and superimposed on the digital terrain. And just so you get a feel for what it's like to fly through this kind of terrain and what kind of issues you might worry about. If there was a cable in the valley, which there might be, I think this data had one, you end up having to go over it. It's somewhat dangerous. But this feels very much like flying in the real world. You'll see that in a minute because I'm going to show you some real flying. So that's the kind of thing we deal with all the time. This has a project in Peru. Next slide, please. So then we talked about how you're going to fly this. And clearly, this is a map that shows slow in black, red in medium, and green is fast. I'm not saying how fast or slow because, quite frankly, it depends on the terrain, whether fast is 80 kilometers an hour or fast is 250 kilometers an hour. It just depends. But the point is that you have to slow down heavily to go up and slow down, and you can't go down quickly. Strangely enough, helicopters don't like to fall down, so you have to go down slowly. So you have to continually vary the speed in order to remain in contact with the ground. Next slide, please. Can you run that one? Okay, this will illustrate what I'm talking about. This is an actual flight in some project in Chile. I want you to keep careful look at this little guy here. That's indicating the forward speed of the aircraft. We'll let this run a little bit. You can see here this is airspeed, which is quite reasonable, 60 knots. The descent rate in this case is 1,500 feet a minute, or 1,600 feet. So it's running along nicely. We're now on our way back up. And we're moving along nicely, but you can start to feel the thing slowing down. Keep an eye on this thing. We'll look at it in a second. It's moving along nicely. We've still got a good airspeed. Just a minute. Now we're going to have a look at the gauges here. Have a real good look at the airspeed. It's going down, down, down. We actually have no forward airspeed in this case. And then you can move ahead and get going again. If you watch right here, you can see that the forward airspeed indicator outside the aircraft is actually not moving. John, you'd be concerned, right? So anyway, that gives you an idea that you have to speed up and slow down, and there are issues involved in wind and so forth if there happens to be some. So we're very restricted in these next slide, please. Very restricted in the flying. Because of the wind conditions, we usually only fly for 3 hours first thing in the morning before the wind picks up. Cables, of course, are a nightmare. In Chile, they're not too badly placed. You can see them. Peru, it's a rat nest of unmarked cables. And so we typically put an observer on board to make sure that the pilot has extra eyes and can concentrate on flying the aircraft, and someone else is helping him find the cables. Next slide, please. I want to talk about the rotor noise, or if you look at the RPM of every helicopter's blade, they're almost the same. Regardless of the type of helicopter, the frequency of the rotation is somewhere around 6.5. At 10 hertz sampling rate, that will give you approximately 1.5 samples per rotation of the blades, the total blades. Oh, by the way, the individual blades have no effect whatsoever. It's the total package. It's like a bar magnet running around. You'll see that that's 1.5. That's aliased. It's below the Nyquist frequency of the actual pulsation of the helicopter. At 50 hertz sampling, you're going to get 7.5 samples for every rotation of the blades. The blades or the whole rotor system can produce between 7 and 20 gammas in a llama. And you can see the others, typically 1 to 5. The R44 is the least affected, but of course we're not using that in the mountains. So it's very important to think about that. Next slide, please. This gives you the typical waveform. You can see if you count, there's 8.49 records. So clearly, this is related to the full rotation of the blade system, not the individual blades pulsing over the helicopter. Next slide, please. This shows you the individual different helicopters. This is what a llama looks like. You can see that the 10 hertz data is heavily aliased. It's not sampling the waveform at all. Next. A star, same story. This is the waveform for real. This is what at 10 hertz. Next one. B2, same. Next one. L3, L206, same. It's actually here you've got a beat frequency that is false. Next one. B6, at least the 206B. Next one. This is the Robertson 44. Practically no noise anyway, and it's not particularly magnetic. Clearly, you need 50 hertz to sample this stuff. Now we'll get on another point. Next one, slide, please. This is a spike that comes in. When the A star falls below 50 kilometers an hour forward airspeed, a fan will turn on. That fan produces this spike and this offset. Can anywhere from 1 to 10 gammas. It's obviously nasty because it's associated with every hill you go over because you're slowing down. Then when you finish slowing down, the fan turns off and it comes back to 0. You have to find these because otherwise you end up with 10 gamma offsets all over your data set. And not only that, they're correlated with topography. So somebody's going to try to tell you their geology. Next slide. That was a beautiful one. This is what they typically look like in the data. We have a system for finding them at 50 hertz. They're easy to find at 50 hertz. Let's have a look at the next slide, see what it looked like in hertz. The 50 hertz data is the red one. The blue one is the 10 hertz. You missed it. And this is a 7 gamma offset to the data. The data comes down here and offsets down and goes over here. So that 10 hertz cannot do a proper job of flying in the Andes. Or under any helicopter, it's not great. But where you have a speeding up and slowing down situation and you need to be able to see that edge that you can correct for, you have to be flying with that. Next slide. This is the last one. So, for best results, you need a helicopter to fly at high altitudes. Safest choice is the A-Star 350B3. By far the best and safest configuration is the Stinger. You need to fly with variable speeds and constantly try to do the best you can. And it's essential to have 50 hertz data sampling. And you need to always be very careful with safety. Next slide, please. Just run it. So thank you very much for your time. I hope some of these little details were interesting to you. I can be found at my booth. You're all welcome to come by and ask me about these things. We've done very well with understanding and safely flying hundreds of thousands of line kilometers in what is probably the most dangerous and difficult terrain to be flying in. I don't think if any of you have been over 12,000 feet, there's not much air to breathe. If you're flying in a helicopter at 19,000 feet trying to do terrain following, it's really dangerous. So you have to be really careful, really safety conscious, and don't play any of the odds. You stick with good weather, good timing, and good health. Thank you very much, everyone, for your patience and time. I appreciate your attendance. Thank you.
Thank you very much, Ted.